Hello, my name is Adarsh Narayanan, and this is Lab 5 Inclined Plane Motion. Our introduction. Investigate a motion of a ball rolling down an inclined plane. Use position data to calculate velocity over time. Compare experimental velocity data from Tracker with a computational model on GlowScript. Determine how well physics models predict real motion. Apply Newton's second law to an accelerating system. And our results. Computational model and observed data almost match completely. Our physics principles. Newton's second law. Net force causes acceleration down the incline. F net equals ma. Acceleration on an incline. Only a component of gravity causes motion. A equals g sine theta. Kinematics. Velocity is the rate of change of position. V equals v naught plus at. X equals x naught plus v naught times t plus 1/2 at squared. Rolling motion. Rotation and translation both affect motion. A equals g sine theta over 1 plus 1 mr squared. I equals 2 fifths mr squared, and by just plugging in your numbers, we get A equals 5/7 g sine theta, and that is our final equation for acceleration. Physics takeaways. Velocity increases over time due to constant acceleration. The motion is approximately linear in a velocity versus time graph. Experimental data may differ slightly from the model. Differences can be explained by friction and measurement error. Our system, the rolling ball, our surroundings, the inclined plane, which is the surface, Earth, which includes gravity, and air, which can introduce possible drag. Our procedure. Record a video of a ball rolling down an inclined plane. Import the video into Tracker. Mark position of the ball over time. Convert position data into velocity data. Create a velocity versus time graph. Build a computational model using GlowScript. Compare experimental velocity with predicted velocity. Our Tracker analysis, which includes our initial conditions. So by using 2 points on from our data, we have to calculate velocity for our velocity time graph. So v equals change in x over change in t. And then we plug in our numbers, and then we get v equals 0.197 meters per second. And we do that for every value on our spreadsheet data to get our velocity time graph. Computational model and our initial conditions. As you can see, this is what our computational model created. So you can see the ball rolling down the incline. But first, our initial conditions. Our mass is 0.2 kilograms. Our radius is 0.05 meters. Our moment of inertia, which is the equation that we talked about before, which is 2 fifths times our mass times radius squared. And then we start the ball at the top of the incline, so we make s equal to 0. We start the position to 0. We have our velocity along our slope and our angular velocity of rolling. And then we have our time settings, which is our frame rate, and our gravitational constant, which is 9.8 meters per second squared. And then we have our while loop. This includes our gravity, but it's on an incline, so we need to calculate along the slope, which includes the angle. Same thing for normal force. And then we have to do rolling without slipping, so our acceleration is equal to the equation that we previously derived. And then we have our force of friction, and then we have our velocity and position over our slope, and then we have our angular velocity. So our observed versus predicted comparison. So as you can see, our predicted speed is a little shifted to the top. So this is because of some possible errors, but it does almost completely the same, which is a really good estimate to how our observed motion will be. Some possible errors. Our friction is not perfectly accounted for. There's an uneven surface of incline. Tracking inaccuracies in video. There are some frame rate limitations because of how short the video is. And then ball is not perfectly rolling, it's slipping instead. Further questions. Does the model predict constant acceleration? Yes, velocity increases linearly over time. Does rolling affect acceleration? Yes, rotational motion reduces acceleration compared to sliding. Further questions continue. What if the inclined angle was increased? It would cause acceleration to increase, and then that in turn causes velocity to increase, and our slope that's on our graph would become steeper. Thank you for listening to my presentation.